Romberg integration is a method of Richardson extrapolation, actually a further improved method of Richardson extrapolation. What we do is, in the Richardson extrapolation, we use two integral estimates to get an improved one. Let's say you are getting this like for twice, two improved integrals we have now. From two initial estimates, we get one improved, and then another two initial estimates, we get another improved. So for these two improved integrals, we get another higher order Richardson extrapolation correction. And when we do this, it's called Romberg integration. So we have these OH2 or square, and we get this with Richardson extrapolation as to the power 4. Similarly, we will get another one, like a similar one, to get another improved one. And we use now these two improved ones that we used in the Richardson extrapolation and get another one. So it becomes OH6, basically. For a special case of H2 equals H1 divided by 2, always use this. Then we will get, in this second combination, we will have this integration formulation with 16 divided by 15 minus 1 divided by 15. And if we get another one of these improved ones and sum them to get another one, so we will get these two improved ones, then we can combine them as well. When we combine them, then again we are increasing the order, meaning that we are reducing the accuracy, the error, improving the accuracy, reducing the error. And in this case, now we have 64 divided by 63 and 1 divided by 63 for H2 equals H1 divided by 2. So it goes like this. You can add another 6 to get 8, then you can combine them to get 10, etc. And in here, in these, M and L are more accurate and less accurate estimates you can think of. So from this pattern, we can generate a general form for Romberg integration. And this general form is defined like this. K's are the iterations, and 4 times the I integration and I integration, j plus 1 and j. K minus 1 are the previous iteration, that means. And 4 previous iteration power minus 1. And K1, 2, and 3 are actually H2, H4, H6, and it goes this way. 4 is H8, etc. So if K is 1, we actually combine these and get this one. So that's just the Richardson extrapolation. If K is 2, then we combine these to get H6. You can get the formulation from here as this one for K equals 2. Put K equals 2 here, you will see that you are getting this one. And for 6 and 6, when you put K equals 3 here, you are getting this equation. Of course, you should think that H2 equals H1 divided by 2. This is important to get these formulations. Other step size ratios, this doesn't apply. For example, K equals 2 and J equals 1. Then here, J is 1, 1, 2. K2, 4 to the power 1 only. I, 2 here, J is 1. And K, 2 minus 1, 1 here. And here, 1 and 2 minus 1, 1, I, 1, 1. Divided by 4 to the power 1 minus 1, 3. So we can set a stopping criterion, as you can see here, an approximation error for the I1K minus I2K minus 1. This time, the previous iteration, divided by the current iteration. So current, previous, current. This gives us a stopping criterion to be able to stop at a certain iteration. We can define an algorithm for Romberg integration so that we can have it as a MATLAB code, for instance, a computer code. Actually, you can see here a function of Romberg. A and B are the limits of integral, an iteration, maximum iteration number, and this is the error threshold. So basically, we have this trapezoidal equation in the first integral iteration. After that, of course, we will have trapezoidal again for the next iteration. Then we will use this formulation and combine these two to get the next one. Then in the other iteration, so we increase the iteration for each time and calculating the formulation, obtaining the integral, then check the approximation error between the current and previous iterations divided by the current iteration. Absolute is better, times 100 gives percentage of the error, and if the error is less than this threshold, then we can stop, or the iteration number is greater than maximum iteration or equal to that, we stop here. And finally, the final iteration number is our Romberg integration estimation. By using loops, this algorithm implements the method in an efficient manner so that you can easily get a good estimate. And Romberg integration is designed for cases where the function to be integrated is known. So we know the function rather than knowing a data or tabular data, because we can generate additional data from the function, and this is good for functions. This is because knowledge of the function permits the evaluations required for the initial implementations of the trapezoidal rule over here. Tabulated data are rarely in the form needed to make the necessary successive halvings. This is important. That's why we are using functions rather than tabulated data for Romberg integration. In this slide, we have example 22, and this is actually the application of the Romberg integration for the higher order integration application for the same integral formula from a equals 0 to b equals 0.8. And remember that the exact value was this. So let's try the Romberg integration in this. Basically, we had these 1, 2, and 4 segments. For Richardson extrapolation, we applied this actually. So these are the trapezoidal rule results, by the way. And for 0.8, only one application of trapezoidal rule. It is very high error. 2 composite trapezoidal rule and 3 of them here. Now we are going to combine these using this H1, H2. This is just the Richardson extrapolation formulation, the first iteration, let's say. In the first iteration, we are using these two. And from these two, we get this HO as the error of h to the power 4. And these are h to the power 2, let's say. Then we combine these two as well. And from here, again, h to the power 4. So we applied this, the same procedure in example 22.1 as the Richardson extrapolation, if you remember. Now, we are going to use the second iteration and use these actually. To use these, so actually this is the first iteration, second iteration, then third iteration, k equals 3. And for k equals 3, if you put everything here and j equals 1, then this result occurs from there. And this 36 here, the lower one, IL is the lower one, is this. And the higher one is this. And from here you get the exact result. When you apply this, because this is h to the power 6, now this is higher than this. That means we will get the exact result anyway. You can see that the Romberg integration with iterations will get us a good result. And we only used actually this data, only these segment values. We don't need to go further, like 8 or 12 with this only by using these 3. Combining them in certain orders and combining these two will give us the exact result. We can show the iterations of Romberg integration in a certain way with a table, as you can see here. For the first iteration, we said that j equals 1 and h is b minus a. So we have these two integrations from trapezoidal rule. Then we combined them to get an OH4 for k equals 2. And here we don't have any other data, so we cannot go further for OH6 for k equals 3. Rather than that, we need to increase the iteration, j equals 2. In this, we have these two from trapezoidal rule. We also had this from trapezoidal rule, because h is now b minus a divided by 2 in this. And from here, we get this equation, this integration with Richardson extrapolation. And from here we have this already, and then we combine these to get h to the power 6. Then after this, we need to go to the next iteration, j equals 3, and b minus a divided by 4. So the h is reducing, like divided by 2 always. So that's the special case we mentioned, and we are always using that. Then here we need another data from trapezoidal rule for h or h square, because we have h equals b minus a divided by 4 here. So we have 3 segments. Combine these two. So we already combined these actually here. That's why we didn't write that again. Combine these gives this. Combine these gives this. And then combining these last two gives this. Then combining this and this gives this one. And this gives this one. So when we can combine these as well, because we have 2 now, and k equals 3 and k equals 4 here. And finally we get the exact result. So this was, in the previous slide we showed this up to here. And even here we have the exact result actually, because h is to the power 6. But here, I mean, this additional implementation gives the exact result again. Then using the Romberg integration with these again gives the exact result. Exact result for j equals 2 where O h to the power 6 and j equals 3 where O h to the power 8, because the function to be integrated is 5th order. The order is lower than this. We mentioned this in the previous slide as well. And the order estimate is 6th order in j equals 2 and 8th order in j equals 3. So if the error order is less than this, then we can get exact result. This means the order of the function. Simpson's one-tree rule would require about 256 segment application to yield an estimate of the integral. You can see here. And Romberg integration produces the same result based on combining 1, 2, 4, and 8 segment trapezoidal rules. Which means with only 15 function evaluations, you can get the exact result. So if you compare with Simpson's one-tree rule, which requires 256 segments to get the exact result, it's just 15 function evaluations. It's much more efficient, you can see. So if you can, please use Romberg integration rather than using Simpson's one-tree rule, which requires 256 segments. So this shows the efficiency of the Romberg integration. It requires an iterative process, as you can see here, and we get the exact result.